Yeah.
Maybe Shiva too.
Twice.
But I would say if anybody here who's not a faculty member, remember Mr. Ray when he was a student, it's time for you to graduate. And with no further ado, I'm going to let Ray go ahead and
thank you, Professor Conrad, for hosting me, and also thanks to Siva for inviting me. It's nice to be back. I used to teach in this building, but on my way from the hotel to here, almost went to another wrong building. Today I'm going to talk about a robust feature-based decision-making problem, aiming at developing a class of optimum policy for this. So this joint work with two of my student collaborators. So Luhao Zhang just graduated from UT Austin. She's going to join Johns Hopkins after taking a 1-year postdoc at Columbia. And Yun Liang is now a postdoc at UT. So given the audience, feel free to interrupt me if you have any questions. So feature-based decision-making has appeared in different forms in different areas of operations research and learning. So for example, in online learning, it's related to the concept of contextual bandits or contextual learning problem. Or in deep learning, it's related to the concept of end-to-end learning. So the idea in this problem is that with the help of big data knowledge, for example, those applications involve e-commerce or those applications with the help of IoT devices or Internet of Things devices, the decision maker is able to collect a lot of information before making a decision, right? And the hope is that with this additional information, which we call the side information or contextual information, or simply put, the feature information, we hope that we are able to have a better understanding of the uncertainty involved in the downstream decision-making task, and therefore make a better decision. So to make this concept more concrete, let's consider the classic news vendor problem in this question. Then on stage, we have a variable y, that is a decision variable that we want to optimize, represent the ordering quantity for a single quantity. Right? So say we want to minimize some operational cost, and set out in this stylized model, we have holding cost h and vector order cost b. Right? So we want to match the supply with the random demand, represented by that, and the news vendor cost is simply put as the plus of the sum of the overage cost and the counterage cost. And for repeated experiment, it makes sense to consider a spectrum minimization problem. So it's well known as the optimal solution for this expected user cost minimization problem is given by the Pareto concept, right? And the F represents the future. So let's think about how this works in practice when we have big data. So practically, the demand distribution could be affected by a lot of factors or features. Not only the demand information in the history, but also say the product features or the shelf features of where the product is located, or some value information or authentic information are available prior to making the order decision. And the goal in end-to-end learning aims to find a map or F, just a map directly from the data X, the feature, starting without explicitly estimating the demand. This is in contrast to a more classic approach that has been used in practice, which is called stated and optimized. And in those framework, we're going to divide our task into two small modules. The first module is a forecast. Basically, we are going to use our favorite machine learning model to estimate the demand function, and typically it's the mean. And after estimating the mean demand model, when the new scenario or when the new feature value arrives, we are going to plug it into our statistical model, and it gives us a mean estimate for the corresponding feature value. But as we've seen in the textbook example on this vendor, in order to make a good decision, we not only need to look at the mean demand conditionally on observation, but also need to look at context, which means that we also need some further information about the distribution of the residuals. And in practice, typically we assume that the residual is normally distributed after getting the mean, we kind of compute the sum of. But this comes with some issues. The first issue is the model uncertainty or model mystification. For example, our mean model could be wrong, namely this function G could be wrong. But maybe even worse, we are looking at not only the mean, but also the residual. The distribution of the residuals could be subject to the inhomogeneous spread of error. For example, just think about at different locations, the spread of the product demand could be different, either at the university or at the city. Right? And for both of models, we can for both of the cases, we kind of need to make a balance between the stresses of the model as well as the computational side of the problem. And the other challenge is based in the feature-based the feature-based decision-making problem, which is sometimes overlooked because of big data, is what we refer to as the small data paradox. So just think of this online research example. It sells hundreds and thousands of products every quarter. According to this study, even you look at the best-selling products, you will observe that almost half of the product category only has fewer than 10 samples within a product. So we usually parameterize or represent a product category by a feature vector. So this would suggest that for many realization of the feature values, we would have we only have very few samples that we need. And a similar phenomenon occurs in, for example, this movie rating example. Although it's a very large data set, but more than 60% of movie ratings has less than 10 ratings. So we represent the movie by their features, vector features. It also means that for many feature realizations, we do not have that many. This is kind of a very common problem seen in practice. And a common heuristic to solve this problem is just to combine different product categories or different so that by aggregating some of the observations, we can get it. But in contrast, in this talk, we would like to have a more principled approach in order to derive a more robust and efficient algorithms for the vision-based decision-making problem. And a lot of results I'm going to talk about today can be applied to more general problem settings, but I'm going to focus on the Newton-Lennard problem as a showcase. All right. So again, in the feature-based Newton-Lennard problem, the idea is that instead of estimating a function g that makes a good prediction in terms of minimizing, say, the square loss of the mean estimation function, we would like to find an estimate that directly minimizes our decision objective. And in this case, it's a Newton-Lennard constant represented by a function psi. And this idea has been central around the past several years, which people want to integrate the estimation and the decision. Right. To make it more precise, so our objective is expect Newton-Lennard cost, and our decision is a function f. The function f kind of tells us for any scenarios of x, how much we should order. Right? It gives us a map. And expectation is taken with respect to not only the distribution of demand, but also the distribution of the features. The idea is that we are not only making decision once, we want to, the manager typically wants to make sure that the average performance over a population of customers or a population of shelves to have a good performance overall. Right? So that it makes sense to look at the performance over both the joint distribution of demand and let me also remark that this psi function, if you think about it, if you're familiar with statistics, this psi function in this particular example, it corresponds to the quantile loss for that used in the quantile regression. But let me emphasize that this is just a coincidence, and in principle, this psi function can be any decision object that you are carrying out. Right, so you can choose any. So the main difference that here we care about the decision object directly instead of looking at some other. Okay, so let me go back to the small data paradox using the empirical quantile estimation as an example. So in this talk example, we have one-dimensional feature represented by the horizontal axis, and this is so the underlying ground truth, consider a conditional median estimation problem, and this dashed curve represents the underlying conditional median, the true median, which is unknown to us. And we take a IV sample, which are represented by the blue dots here. So suppose we have a continuously distributed feature and demand. And therefore, as you can see here with the property of 1, all x values will have distinct values. And this occurs with property 1 if you have a continuous distribution. This also means that for every x value you have seen, it only corresponds to 1 demand data point. And therefore, the conditional demand distribution given any x would be just the 1-point distribution, and the corresponding amplitude quantile would be U-defined, right? And this phenomenon occurs not only for continuous distribution. If you have, say, a distribution with finite number of outcomes, say you have a 10-dimensional random variable, and for each component it has, say, 5 outcomes. Then there could be up to 5 to the power of 10 different combinations. And for a reasonable data set, it's impossible to exhaust all possible combinations, let alone for every combination multiple observations to have a better estimate about the expectation. Right? And the other issue is not only we care about the mean sample performance, right? We look at the L sample extrapolation. So as you can see from this example, the simple linear interpolation will not work because it has too many features. The toy example tells us that it's 2 things. So one is for the in-sample values, we need a better estimate of the conditional. And second, for those unseen feature values, we need to think about a better way to estimate. Right? So let me talk about 2 existing approaches in the literature that deal with this problem. Non-parametric and parametric. So the non-parametric is kind of a mainstream of this literature on joint estimation and joint estimation and prediction. So basically, they use a lot of tools from non-parametric statistics, such as local linear regression, nearest neighbor or forest or ensemble-based method. So aim to just use this idea to have a better estimate about expected unit center cost given the observations. So it is model free because it does not have an explicit form on the demand function. But on the other hand, it actually does not directly minimize our decision objective, which is unit center cost. So let me explain it again. So if you think about it, all of the above mentioned approaches do the following. So on the right side, suppose we have collected data to estimate the conditional unit center cost for every observation, etc. And if for a new feature X, we are going to estimate its cost under a given ordering quantity Y using a weighted average of the observed conditional expectations. And the different approaches differ from each other by choosing a weighted WI. And if you think about it, even if, say, we have the precise estimation about the conditional expectation, say the true expectation, their weighted average, in most cases, does not give the actual expected cost under a new sample. Just give us a circular model for the cost based on weighted average, but it does not utilize the explicit Nussbaum form and does not give us the precise. Right? So essentially, what this non-parametric model does is that it look at this circular model, and because for this circular cost, it is very easy to minimize it over the Y, and the optimal solution would give us a non-parametric estimate of the. So the other approach, based on parametric idea, is that we know that say because optimizing over an infinite dimensional estimator is very hard, so instead it restricts the policy class to say a parametric one, which is easy to solve. You can choose a small class such as the affine class, which is tractable, very tractable, and easy to generalize, but it suffers from suboptimality because hardly ever you can see an example where the optimal quantile is an affine function of the feature. Right? Of course, you can limit the space by using nonlinear transform of the features, but the issue is that sometimes, actually quite often, the lifting, the nonlinear transformation is hard to interpret. The most extreme case that is you can use a neural network, right? As been shown, empirical data has a good performance. But beside the interoperability issue, is data demand. And think about the example that we talk about. Actually, even for this problem, we may not have that many data just to train the neural network. To summarize, so the parametric approach kind of balances between the suboptimality of the policy class and tractability and interoperability of the corresponding problem or the policy. So having this discussion in mind, I would like to answer the following question. Is it possible to find an optimal policy without restricting the class, but at the same time maintaining interoperability? And our proposal would be to look at the distribution robust policy formulation. So idea is as follows. So let's consider a min-max robust formulation. The decision is still a map, the decision a policy that we want. Okay? But we add an inner maximization problem, kind of evaluate the worst case risk or worst case cost under different distributions. So we are going to look at a certain set of distributions, which consists of some distributions that we think are relevant to our decision-making problem. Right? So typically it's going to be measured by distance. So we use some distance to measure similarity between probability distributions. So the p hat is the training data we have, and we want to look at some distribution around it. So the choice of uncertain set now goes down to the choice of the distance. So let's recall the degeneracy issue that we have seen from the empirical quantile estimation problem. Right? One of the issues we discussed is that somehow we need to hedge against the uncertainty on unseen samples. So therefore, for those type of problems, it makes sense to consider the distance that is based on optimal transform, such as the Walton-Stein distance. I did not include the mathematical formula for Walton-Stein distance, but I hope I can convey the idea or intuition behind Walton-Stein distance. So let's look at the two distributions. The blue one is the uniform distribution on those blue dots, and the red distribution P is the uniform distribution on the red dots. So what the Walton-Stein distance does is that it measures similarity between the two probability distributions, and the smallest effort we need to perturb the red dots to the blue dots. And the effort is measured by the pairwise cost or the total cost between the points. Right? For example, in this two dots, and they are kind of similar to each other, so their cost will be small. And for these two dots here, their distance will be further away. Kind of measure similarity between samples, and the Walton-Stein distance finds the cheapest cost of transporting property mass from one. So you think of the observation and the perturbation of the underlying ground truth. So it makes sense to look at distributions with different form and use the Walton-Stein measure of closeness between property distributions. This is kind of one of the advantage over the bilateral divergence or total variation distance. Okay, so let's talk about the challenges involved. Yes.
Quick question before you go on. Can you go back to the previous slide? Yes. So I think you made a very good case that often the data that you have to estimate, say, the different distributions is very sparse because X can be continuous or X can be many different X's. So in this case, what is your nominal distribution?
Yeah, it's gonna be the joint distribution over the feature space and the demand space. It's gonna, but in this case, it's a two-dimensional space. Yeah. Any other question? Okay. So for this min-max problem, so actually the inner maximization problem has been well studied in the literature. It's just the Walton-Stein DRO problem. In the past, say 5 years, there are a lot of work in this area. And actually, so here we do not restrict the policy class. It can be any function. So this result would apply to the setting to derive a dual formulation. So the main challenge of this problem actually lies on the outer minimization problem, which is another well studied in the literature in theory. So in the literature, it's belongs to a class of so-called adjustable robust optimization or adjustable robust counterpart. So this is a small paragraph I quoted from the famous book, textbook on robust optimization. So for the ARC, the just robust counterpart, typically is very intractable computation. And really exactly similar to what I have discussed for non-parametric optimization. It is an infinite dimensional problem. We are optimizing over policies or over decision rules. So therefore, even when we started the project, our first thought is just to look at, for example, the IFAN decision. Right? And the only exception is that if you can identify some structure of the optimal policy, then there's a hope to reduce the infinite dimensional optimization problem to a finite dimension. And luckily for this problem, we are able to achieve that. Right? So next slide, I'm going to show our main result, but before I go to that, to see if there's any questions regarding the setup and the framework.
You can identify the Bonnet class, so then the problem reduces to the regular distribution robust, or there's still other challenges?
It can be viewed as a distribution robust problem still, but the solution method would be a little bit different. Because here you want to solve the entire min-max problem in some way, instead of only look at the inner max problem and think of the alpha one as a parametric optimization. I mean, how we parameterize the problem is kind of different as you see. Yeah. Okay, so the main result states as the following. In order to solve the entire min-max problem, we are going to do it in 2 steps. So in the first step, so let's solve for the so-called in-sample robust problem. Right? So in this in-sample problem, so the main difference is that we are going to restrict the support of the distribution and the feature distribution on only the in-sample values. If you recall, the main difficulty of the original problem originated from the fact that the f function, our policy, is defined on the entire feature space, which could be infinite, right? But now by restricting the support to only the in-sample problem, to only the in-sample data, it boils down to the finite dimensional problem, because you just need to decide the value of the in-sample. Right? And this problem becomes a finite dimensional problem. And turns out, as you will see later, it actually can be reduced to a linear program, which can be computed efficiently. I'd also remark that here, I only restrict the support for the features, but not on the demand. So for demand Z, the support could be still the original space. And this solution, at start, gives us the optimal robust in-sample policy on those observed samples. Then the next step would be to extrapolate it to all the other unseen features. The way we are going to extrapolate it is based on a new attribution method, which we didn't find in the literature, but we name it as the Shapley policy, and I will explain shortly. Yes, question.
Okay, just a quick question. So earlier you said the nominal distribution is not a joint distribution of features and decisions, right?
The feature and the demand.
Features and, okay, random variables, yes. And let's suppose it's sparse, like in your earlier examples. Mm-hmm. So for every feature, you have only one observation of demand. Mm-hmm. So then this reduces to just for each one of those observations in your data set, compute what the optimal decision would have been.
Yes. Sort of in that way, but here, because you do not restrict the support of that, so therefore, you need to kind of balance different distribution corresponding to different depths.
Let's go back to my other example. Let's suppose for each feature, you have only one observation of demand, like in your sparse, your sparse argument. So in that case, again, for every feature, there's only one observation of demand. So then the optimal solution, the F star there, is just whatever is the optimal decision for that particular feature of demand calculation.
Not exactly. I'm going to show you in a second by a figure. Over here. So these purple dots are the solution for the in-sample robust problem. And the idea is that because, I mean, essentially for this in-sample problem, the only thing can change is the weight that you put on each of the in-sample feature. And the location is fixed, but the weight on every point can be changed because we only restrict the support, but not on the weight of each of the in-sample feature.
But let's go back. Let's suppose, okay, so again, you have weight of 1 over n. N is your data size, right? So the nominal distribution has weight 1 over n on each combination of feature and demand. Even if you change the weight, the optimal decision doesn't change.
The problem is not separate. So you cannot look at each individual conditional optimization problem separately.
Why?
It is linked by, so for example, mathematically, if you write the rule of the problem, the different ways are connected by the distance. You can still move the probability around, right? So it's not a separate optimization problem.
No, but even if you change, so M hat is just, all you do is you change the probabilities you put in those combinations.
Right. Yeah.
But if for every value of the feature, you have only one observation of demand, changing those weights makes no difference. Right? Because you're estimating a function from X to the decision Y. Right? And for every X, there's only one value of demand. Whether you put a weight of 0.1 or 0.9 on that demand makes no difference. It's the only demand that you have for that feature value.
Yeah, so let's, for example, look at this example.
Yeah.
Say, for this point, it corresponds, or maybe for this point, this is the conditional empirical quantile. If you make your decision in this form, because you can change the weight, then you can move the in-sample feedback a little bit around. This point is so large that if you move further away, say to some adjacent features, it's gonna give you a larger Newton-Meter cost because now you're allowed to move. I mean, well, when I talk about move, it's about moving the decision, not moving the.
But I thought you said M hat just keeps the support the same, it only moves the probabilities.
The support in the in-sample features, yes, but only the weight. So name that you can move a tiny proportion of the weight from one feature to the other, right? And the same quantile will give different values. The same value of ordering quantity here will give different values for different feature validations, even for in-sample. So for example, this point gives a 0 in-sample value for the corresponding X, but give a non-zero in-sample cost for different feature values. So the problem itself is not separate among feature values.
So that doesn't make sense. You make a decision for a particular feature, right? F is a function of, the decision is a function of the feature.
Yeah.
So I make it for every feature, I have a decision, right? And for that feature, you have only one observation of demand.
Yeah.
Whether you move the probability mass to other observations doesn't change the fact that for that feature, there's only one value of demand.
Right. Only one value of demand, yes.
So even moving probability to other features, probability mass to other features, does not change that for that feature, you're going to make a decision, and for that feature, the only observation of demand is the one that you have in your data set.
Okay.
So I don't understand why moving probability mass to other features changes the optimal decision for a particular feature. I'm sorry, I'm interrupting you. We'll discuss this afterwards.
I mean, no, I'll have to explain. So say for this particular feature, you are going to choose the empirical quantile as your optimal organization. And it's true that if you, by moving the feature value around, it will not affect the in-sample Newton-Meter cost corresponding to that feature. But when you take the weighted average, now you are allowed to move around the probability mass, and it's going to change to a different objective, right? The weight in front of different features will be different. And the same decision would give you a different objective if you change its weight.
Let's go back. Okay. Let's talk about this afterwards.
Okay.
Okay.
maybe there are other viewpoints to look at the problem from the regulation point of view, for example. That tends to be unclear.
Can I ask a quick question?
Yeah.
If you go to the next slide, the one. Yeah, just curious, the reference description you're talking about is empirical, right? Okay.
Yes, yes.
So I'm just curious about this because it's like interdimensional observation. So do we have convergence of, let's say, if the radius goes slower, it's going to, going to converge to true problem?
Yes, you have the consistency for the original problem. But we should be cautious that it's essentially a non-parametric approach. So as you can imagine, the convergence rate will have a non-parametric rate. Namely, you have a curse of dimension. Because you do not restrict the policy class to be a parametric one. So you not enjoy a parametric rate.
Yeah, just a follow-up for this, right? So if this is overfitting, I'm just wondering, right? If you have let's think about the SAA version, right? Then you essentially have overfitting for each point.
Yeah, for the SAA version, just the blue dots we have said, right?
Yeah.
Yes. So that's why this kind of adding robustness helps to reduce the overfitting issue.
So you are saying, if some side is going to infinite, the SAA and the robust small set is going to be coincide, right?
The issue with SAA is that it is not well defined on those unseen feature values. So even if you have a very large amount of data, so then therefore you have to be careful in defining what convergence really means, because you're comparing what distribution, the truth distribution could be defined on the entire space, but your SAA solution is only defined on the points.
I guess, yeah. So in this case, the robust model has convergence.
Yeah, this gives kind of a qualitative difference between SAA approach and robust approach, right? Robust approach is well defined on the entire space, but the SAA approach only well defined on the in-sample points.
Okay. So another question about the policy. I think you're talking about the old policy. Suppose I have some preference of policy. I guess some bound of policy, it still works.
Yes, if you have a bound, that works. If you want to constrain, for example, order quantity to be within inside the interval, the result will follow. Any other questions? So let me remind you that the two steps actually correspond to requirements that we have seen from the slide example. So the first one gives us a better estimate, a more robust estimate of the conditional demand on in-sample values. And the second one, the second step gives us a better extrapolation on those unseen feature values. So let me illustrate this sharp extension. So in the first step, what it does is actually to compute this in-sample robust values on those observed samples. So this purple dot kind of gives us an estimate for the in-sample. And in the second step, it extrapolated to all other features in some special way. So if you compare the blue curve with the purple curve, the purple curve seems to be more close to the brown curve. So let me define the Shapley policy mathematically. So for a new feature X, we are going to define our Shapley extension F star in the following way. So we pick so here X is fixed. So let's introduce a matrix, AJK. Right? The indices J and K represent the indices of the in-sample points, X hat J and X hat K. So essentially, this AJK is nothing but the weighted average of the previous computed in-sample robust policy in the first step. See that if the new feature is close to the J sample, then it's going to put more weight on the in-sample robust solution corresponding to that sample, and vice versa. And in the second step, we are going to define our policy as essentially the matrix set point, a pure equilibrium of this matrix, which is whose existence is proved using the Shapley theorem in game theory. So that's why we term this policy as a Shapley policy. Right? So to illustrate, so let's consider the case where we have three data points. Right? We have three in-sample features, and this y-axis kind of represents the in-sample robust solution. So instead of the in-sample conditional observation, these are already the computed robust solution that we get from the first step. Right? So after getting the in-sample robust policy, let's compute A12, for example. So if X, the new feature is in between these two in-sample features, then simply the weighted average is just the linear interpolation. And outside the range, you can see that it actually converges to the average of the two in-sample robust policies. But the idea is that if you have a feature that's very far away from the in-sample observations, then basically the in-sample information will tell us only little information about what it should do for a very further away feature value. And the safest way to make a decision is just to look at the average of the. It's kind of the idea of say the Bayesian analysis where you have uniform prior, right? And similarly, you can define say A13 linear interpolation in between, and you have in the infinite you have converge the average of the two. And you can define A23 in a similar way. And after obtaining A1 to A13 and A23, you compute the corresponding matrix set point for each of the X. Turns out it's going to be the middle curve. The intuition is that when you make a decision, order decision, you do not want to make the extreme order either too much or too low. That kind of give you some unpleasant scenarios in extreme cases. The more safe or more robust version is to look at some middle values. That's kind of the So the other way to look at this formulation is from the regularization perspective. Right? With some additional analysis for this problem, you can actually show that the min-max robust problem is equivalent to the following Lipschitz regularized problem, where the first term represents, say, the empirical instrumental cost for a particular policy F, and the regularization term penalizes the Lipschitz norm of the policy. Where if you have a policy whose Lipschitz norm is very large, that means that a small perturbation of data would lead to a very large change in the cost, which is not good, right? So therefore, the robust problem kind of balances between the in-sample problem, the in-sample cost, as well as the Lipschitz norm of the policy. And indeed, if you compare the Lipschitz norm of the blue curve and the purple curve kind of solves the zigzag issue that I have seen from the blue curve. Right? So in summary, just the robust policy carefully balances between the deviation from the empirical quantile, namely blue dots. You want to drag it a little bit to the middle so that you can achieve the small Lipschitz norm. So if the variation measured by Lipschitz norm is small, it would entail that the solution would be more robust against the data population. So the next comment that in the literature, it has been well known that the robustness is connected to regularization. But let me emphasize that all those conditions in the literature, even for the most general one, is not satisfied by this problem. So to get this conclusion, you have to pick out the problem to prove its equivalence. You cannot use any existing equivalence. Essentially, because its F is arbitrary. You have to carefully look at the optimal structure of the problem.
So you're saying, so your method of using the min-max convex combination solves that problem on the screen?
Yes. Yes. But probably from this point of view, that explains why the in-sample purple dots is different from the in-sample blue dots. So let me give you some intuition behind the proof. It's not the actual proof, but I hope this intuition conveys some of the idea from this problem. And maybe hopefully ask you a question. So the idea is that for the in-sample problem, because we are restricting the uncertainty set, so we have the less than or equal to relation naturally. So the main issue is to look at the other side, right? So if you think about it, so actually what the in-sample problem does is that by only looking at those in-sample points, it carefully balances between the in-sample objective, the new standard cost, and the variation of the policy on those in-sample points as measured by the empirical Lipschitz norm. So for example, if you choose the policy to be kind of extreme value, their empirical leaf norm will be large. In order to make their empirical leaf norm to be small, you need to drag some of the outliers down to the middle to make your decision more robust. Right? And the explanation we did in the second step actually solved the following slope minimization problem. So basically, for a new feature x, we are going to decide the ordinary quantity of y as a solution to the following problem, where this ratio represents the slope of the line connecting from the existing observation and the new feature. Kind of represent the slope of the line. And then you look at the maximum slope among all data points, and you want to choose the ordinary quantity that minimizes such slope. And it can be shown that such a definition, the slope minimization problem actually preserves the leaf norm. So namely, if you solve the incident problem and get empirical leaf norm for the problem, then such extension will use the policy that has the same leaf norm in the entire space as the empirical leaf norm. And the third step, it can be shown that actually the Schacht's policy we define as the center point of the matrix actually solve the slope minimization. Right? So let me use this kind of geometric idea to illustrate why this is the case. This is my first time to talk about this. Hopefully I can make it. So we are going to use a point to represent the line or slope of the line to represent the quantity on the right side. So the horizontal line represents the distance to the new feature. The new feature is x. For example, if I have a point here, they can represent the new point at one point. Actually. And all the others kind of represent the distance of any existing samples to the new sample. Right? You can see some of the points are further away, some of the points. And the y-axis represents your policy. Right? And therefore, those purple dots and the orange dots represents the existing distance, the distance of the observed samples to the new feature, as well as the corresponding in-sample robust policy. So now the problem of finding a decision y for a new feature in this figure just represents that you want to choose a point on this y-axis. And for any point, you connect with any of the in-sample points. And the slope of the line, the absolute value of the slope of the line, gives you the ratio. So for example, if you choose the y here, and you can compute the slope. And you're going to look at the slope of every connecting line and want to choose a position of this line, of this line, so as to minimize maximum. So another way to think about it is that you're going to put a flashlight on the y-axis. And this flashlight gives you a light beam. And you want to make sure that this light beam, the angle of the light beam is large enough to cover all points that you have observed. Right? For example, for this, if you choose this angle, all the points on the top can be covered, but some point down below cannot be covered. So that does not give you a solution. Right? But introducing, for example, a mirror on the y-axis, we can actually represent the sum of the quantities that we have seen in the matrix definition. For example, it's AJK. The way we interpret it is as follows. Think about that you're standing at this point K. And you're looking at the image of the J point from the mirror. And this is how the light traverses and reflected. And actually, this point, the reflection point, is the value of AJK, just by symmetric arguments and the physical logic. Right? Now I'm standing at the case point and look at all the images of the sample points. And the largest reflection point is in the largest value among overall objects. Right? And again, we want to choose the position of flashlight so that the light beam covers all points. Right? And apparently for this position, it's too high because the slope upward is reasonable, but in order to cover all the points, the slope downward is too much. So therefore, in order to solve this problem, we need to have a careful balance between a position and the angle. And the solution for this problem just gives you a set of points. Namely, for all the highest reflection point, we are going to choose the lowest one so that the downward slope and upper slope would be the same. And this light beam covers exactly all points. And the kind of the margin or the edge gives you the solution to this problem, or gives the optimal value for this problem. Right? And because you can either standing at this point, look at all the other points. So therefore, because of symmetry, you can change KMJ. The kind of geometric shows that Y has a second. I am pause here for that to see if I can convey this slide. All right. So I have 10 minutes just to show you some numerical experiment. So we conduct experiments using both real data and synthetic data. So the benchmarks are either using IFM policies with regularization on the coefficient, or some non-parametric approaches. The kernel density estimates, some Fourier space approaches and their variants, and the k-nearest neighbors. Right, so in the synthetic data, we are working with a large dimensional problem. So the dimension of the features is 5,000. We designed the correlation matrix so that some of them are highly correlated and some of them are. So the true coefficient is sparse. We have 400 non-zero values. And the noise is the standard Gaussian transformed by a nonlinear exponential function. So our testing data set is large, and our training data set is relatively small. All the hyperparameters used in the benchmark as well as our method are tuned by a five-fold cross validation. We're going to fix the backorder cost and vary the holding cost so that we are going to see different quantum.
Is the dimension.
Is the dimension of the feature and the same dimension of the beta as well. But it's a sparse problem, so that actually 1,000 is kind of relatively larger than the sparsity of the problem. But the other 10 or 100 is a relatively small dimension.
So N is the number of non-zeros?
And the number of training samples.
What is the number of non-zeros in beta?
400.
Yeah.
Okay. So from this result, so basically the y-axis represents the difference in L sample cost between the benchmark and our approach. So a positive value means that our approach is better. This bar plot kind of represents the distribution of the differences in 20 repeated experiments. You can see that across most of the experiments, the Shapley policy performs better in terms of the L sample performance, either the median or some of the quantiles of the box level, right? The only exception occurs here, right? It's a conditional median estimation problem because the holding cost equals to the factor order cost, and have a 1,000 sample. This kind of gives a kind of a large sample problem or a big data or problem with sufficient samples because we only have 1,000 samples, but we only have 400 non-zeros. And in this case, actually, even for linear regression, it performs good. It beats actually all other non-parametric approaches. So let's talk about the computation time. So we have a training time and testing time. So the training time means that given the training parameters and how much time we need to train a model using n sample. And testing time is for the full testing data set, how much time we need to get the optimal decision. So let's look at the training time first. So for the Shapley policy, because it's gonna be solved using linear program for both the in-sample problem as well as the L-sample explanation. So the computation time is comparable with two other approaches based on linear program or convex combination. So the first approach does not work very well. But for the non-parametric approach, essentially does not need any training, right? Because just need to set up the function. Because all time it takes is on the testing period. Okay. So for testing time, you see that our approach is better than all the non-parametric approaches, although our approach is still non-parametric. You may observe that it does not scale very well in terms of the sample size, but I like to mention that here, it's not because solving the linear program is not fast, just because to set up the problem, set up the cost matrix between pairwise differences, it's a kind of takes some time. The overhead cost is right, but still compared to all the non-parametric approaches, it's faster. So the FI decision rule is very fast, regardless of the dimension of the problem, because you just plug into the function.
So why the testing time is longer than the training time?
You mean for the Shapley policy?
Yeah.
Because to get the testing, to get the policy for a new feature, essentially you're doing the second step in the algorithm, which also involves a linear program. Essentially, it solves this problem.
I see.
Yeah.
Have to compute all the HAKs. That's the.
Yeah, the overhead cost comes from the in-sample to set up the problem and make it into the group. Yeah. Because yeah, essentially you have n number of points, and to make it to load it as a model, it takes some time.
What's the range?
The K is the index for the in-sample point. So here, the running time for the Forest-based approach is marked by a star, because for testing, it actually takes much longer than the threshold. So we actually consider a simple, a kind of a truncated version of the problem. In the next example on real data, you see that actually it takes a very long time to even for the moderate size. So here in the real data set, it's a company that sells the basket. It's a relatively small dimensional problem, only have a 40 dimension. And the setup would be similar, but we vary the sample size in the training data set to be smaller, equal to, or larger than the dimension of the variable. And the technical data set is also a real data set, and the rest of the setup will be similar. So for some reason, it's surprising that we actually found that for a real data set, the gap between other benchmarks and our approach is even larger. But the same intuition holds. You see that for the large data size and for the conditional media estimation, because the sample size is very large, so even for the economic model, in those cases, it does not bother to look at the robust, right? And by looking at this computation time for both training and testing, you can see that actually the forest-based approach does not scale very well, even for testing period. So among all the non-parametric approaches, the kernel density estimate, the KNN, and the forest-based approach, let's see, our Shapley policy kind of computer optimization in the real time. So let me summarize this talk. So basically, we propose a non-parametric end-to-end policy automation for the feature-based expander. And it solves for the optimal policy without sacrificing the trackability and interoperability. And I talk about the business problem, but actually all the results hold if you have a convex clause that's convex in decision, and have arbitrary dependence on the random variable. And one good thing about this approach is that it does not confine the dimension of the features. But on the other hand, the decision has to be one dimension, which is kind of a downside. So if you think about it, to extrapolate a real valued function is well defined. But how to extrapolate a vector valued function is not a well-defined problem. So, which kind of, and actually for multidimensional problem, there are counter examples shows that it's kind of impossible to reduce the infinite problem to a finite dimension. And with that, I conclude my talk. Happy to take any questions.
Q&A questions, comments?
The last point you made, are you saying like if you have a problem that's like has 2 dimensions for its decision, you can't apply the Shapley technique?
The Shapley policy is defined originally by the matrix set point. You have a vector value. You don't have the matrix. You have a tensor, right? But on the other hand, this problem is still well defined. You can replace the f value by the norm. But the slope minimization problem, the slope minimization policy, is not optimal for a certain instance. There are some countries. But for some problems, it still works. I'm thinking of this in the context of multi-stage programming, and sometimes it works.
Then can you just say again, so that problem is still well defined, right?
Yes.
It's just that your HAK values don't solve that problem.
No. Yeah, right. But that problem is maybe not optimal for some instance. You cannot show it's automatic for the original problem. Or you can prove that it's not optimal for the original problem.
Yeah. But that's what do we mean by original problem is the one with the regularized version that you had up there.
Either regularized or the mixed version.
On the regularized,
for the min-max, because in general they are not equivalent.
So that's the issue. It's the issue that the min-max and the regularized version are not equivalent.
Yes, right. So let me remember. If you solve for the I think the slope minimization problem. The leaf regulation problem is still very remarkable. It's still tractable because this slope minimization problem preserves the leaf norm even in high dimension. Right. But it just not solve the original min-max.
If I have derivative information or derivative constraint, will I be able to use this?
Good point. Essentially, you are going to extrapolate it not only from the Lipschitz norm, but also say, I don't know, second order.
Yeah.
I think it's going to be related to the SIF method in some way, but I did not dig into that direction anymore. Yeah, there could be some connection, but still, it's a non-parametric problem, whether it's solved or not.
Or this may be naive, but it said this method only works when like your next feature is in between different features. For example, let's say I'm predicting the overall GDP of all human beings, and then my only predictor is time t. So it looks like a straight line going like higher and higher. But if you predict for the next time point, it always goes like back towards the average, right?
Right. Kind of how it behaves in the limit is kind of the average of all things. Yes. just choose like the kind of similar to the Chinese philosophy, just something in the middle.
So just I want to hear your opinion about this. So go back to your comparison with predict and optimize. Right, so I think it's a natural thing to ask, instead of predicting some model, calibrating a model, then optimizing the model, why don't we just try to directly predict an optimal decision? Okay. And I think there are at least two reasons why this might not be a good idea. One is that for some types of optimization problems, even simple ones like linear programs,
gradient-based method will not work.
that's because the optimal objective value might be nice and smooth with respect to the parameters, whereas the optimal decisions are discontinuous. And another reason is because sometimes we have data to calibrate a model, right? Like demand data on your example. But to calibrate an optimal decision, we don't have observations of optimal decisions. Right? Even if it's practical data, the decisions in the data set are not necessarily good decisions. So we don't have optimal decisions. We can just put a model of optimal decisions as a function of features.
Right. I mean, in reinforcement learning, like imitation learning, people want to kind of learn from the expert behavior. But even for those applications, probably the better way for George will probably have more input. The better way is just learn, say, the Q function of the reinforcement learning instead of the decision. Because the relation between the decision and the parameters are typically not very they behave not in a smooth and nice way.
Yeah.
But for the value function, they behave better. That is the use approximation.
An example of the second one is training of self-driving cars. Right? They train the self-driving cars by humans driving the cars. But the humans drive bad, so now the self-driving cars also drive bad.
In that case, probably you want to regularize in some way.
Do you have any guarantees, like if your observation increase, and how this out of sample, cost, you're getting closer to the truth?
Yes. So yes, we have a results in the paper, but basically, I mean, it is measured by because this problem is related to Lipschitz gradation. So essentially, you are working with the family of Lipschitz, and it's very much back to the that's how we get the algorithm performance guarantee.
So this is basically related to the expressiveness of Lipschitz continuous functions.
Right. Exactly. Yes. And actually, how they derive the radiometric complexity for Lipschitz class is based on computing the Wallerstein distance, because the one Wallerstein distance have this correspondence.
All right, any more questions, comments? If not, thanks again, Ray.